Electricity is one of the fundamental forces that power our modern world. From the simple act of turning on a light to the complex workings of electronic devices, the flow of electric charge is at the heart of these processes. This chapter introduces the concept of electric current, exploring how charges move, the factors that affect their flow, and the principles that govern the electrical circuits. At its core, electric current is the movement of electric charge, typically carried by electrons in a conductor such as a wire. The flow of charge requires a potential difference, which we normally call voltage, to drive it, much like water flowing through a pipe due to a pressure difference. Understanding electric current is crucial for studying circuits, power generation, and other electronic devices. In this chapter, we will talk about electrical battery, electric current, Ohm's law, resistivity, electric power, and power in our household circuits, a brief overview of alternating current, and a microscopic view of electric current as well in the conductors. We will conceptually try to understand electrical conduction in the human nervous system. We begin our study of electric current with the very basic of understanding an electric battery. Volta's research found that certain combinations of metal produced a greater effect than others, and using his measurements, he listed them in order of effectiveness. There was an electrochemical series that was built by the chemists. He also found that carbon could be used in place of one of the metals. So Volta conceived his greatest contribution to science between a zinc disc and one of the silver. He placed a piece of cloth or paper soaked in salt solution or a dilute acid and piled a battery of such couplings on one on other as making a pile. This pile or a battery produced a much increased potential difference. So indeed, when strips of metal connected to two ends of pile were brought close, a spark was produced. Volta had designed and built the first electrical battery, and he published his work in 1800s. So it's nearly more than 2 decades, more than 2 centuries. So this is a sample of the electrical cell or a battery. A battery is when many cells are combined together. A battery produces electricity by transforming chemical energy into electrical energy. The chemical energy, due to the reaction between the zinc electrode and the sulfuric acid, produces transfer of electrons from one to the other terminal, and hence there is a difference in potential. The simplest batteries contain two plates or rods made of dissimilar metals, which we call electrodes, as you must be aware from the chemistry lessons that you must have taken before. Such a device is properly called as a cell, and several cells, as I already said, connected together form a battery. Sometimes we also use the word battery for a single cell, also in today's world. The chemical reactions involved in most electrical cells are quite complicated. So the cell that is shown in this figure, we use dilute sulfuric acid as an electrolyte. One of the electrodes is made of carbon and one is of zinc. The part of each electrode outside the solution is called terminal. So what we see in the modern batteries, we have a positive terminal and we have a negative terminal in our batteries. These were the very first cells where we had solutions in it. So the acid, the part of this, the acid, that is, we have the sulfuric acid, tends to dissolve the zinc electrode, and each zinc atom leaves 2 electrons behind on the electrode and enters the solution as a positive ion. So the zinc electrode thus acquires a negative charge, and the electrolyte becomes positively charged, which can then pull the electrons off the carbon electrode, and carbon electrode hence becomes positively charged. Thus the carbon electrode after attaining a positive charge, and zinc electrode attaining the negative charge sets in a potential difference between the two terminals. In a cell whose terminals are not connected, only a small amount of zinc is dissolved. But if you start connecting the terminals, you probably, the reaction is increased. If the zinc electrode becomes increasingly negative, any new positive zinc ions produced are attracted back to the electrode. Thus, a particular potential difference is maintained between the two terminals. After a time, when this reaction is complete, or one or the other electrode is used up and the cells become dead, the voltage that exists between the terminal of a battery depends on what the electrodes are made up of and their relative ability to dissolve or give up electrons. So, a battery transforms chemical energy. We don't have to work on the chemistry part of it, but we can know from basic fundamentals that a battery transforms chemical energy into electrical energy, and chemical reactions within a cell create a potential difference between the terminals by slowly dissolving them, just as we looked at the previous slide. This potential difference can be maintained even if current is kept flowing until one or the other term is completely dissolved. That's what we were talking about. So, even in our electrical cars, considerable amount of research is being done to improve batteries for electrical cars and for hybrids. One such example is Tesla. One type of battery is lithium ion, in which the anode contains lithium and the cathode is carbon. Electric cars need no gear changes and can develop full torque starting from rest and accelerate very quickly and smoothly. If you own a Tesla, you know if you suddenly press the accelerator, it kind of accelerates really fast. In our picture over here, it shows that we have a D cell, and one of the cells, when it is combined with another cell, we have two AA batteries over here. So we use these kinds of combinations in our battery, that if we connect a bulb to it, it has many uses. So the cylindrical zinc cup is covered on both the sides. Its flat bottom is the negative terminal and the projected up terminal is a positive, which is actually carbon electrode. And if we combine the two these are the dry cell categories, in series, then you increase the potential difference of the terminal, and hence the bulb will grow brighter. So we come now to the what is the basic definition of electric current? The electric current is the rate of flow of charge through a conductor. If I have a conductor, and if I'm trying to look for the definition, then it must be the number of charges that are flowing through the conductor per unit time. That's how we define the electrical current. The purpose of the battery is to produce a potential difference, and the symbol of the battery is shown like this. The positive terminal is longer and the negative terminal is shorter, and we write the negative sign on the negative terminal. So this is the symbol of the battery. The device connected to battery could be a light bulb, a heater, a radio, or some other device. So once we connect to the battery any device, so maybe if I connected a bulb, the symbol for the bulb, it will start glowing because a potential difference is dropped across it. That means the charges might be flowing from the battery's terminal and then entering through the other terminal. Hence, a series or a flow of charges per unit time is established. Normally, the electrical current back in time, we call this as conventional current. It is actually the positive charge, positive terminal is not the direction where from the electric current flows. It actually, in reality, it's the negative terminal is the one where from the electrons travel. But back in time, we used to it was established that it's the positive terminal that's actually the charge carrier. So based on the findings, the SI unit of current was named after a scientist called Ampere. So A stands for ampere. And we already know that Q, the charge, has the unit named after the scientist Coulomb. So if current I is charge per unit time, the rate of flow of charge per unit time, the units will be Coulomb per second, which in short is named as ampere. Hence, you will see we write the symbol A with the current. So 2A means 2 ampere current, 3A means 3 ampere current, and so on. Or 2MA means 2 milliamp current. Or if you go to a further lesser value, 2 microamp, which will mean 2 cross 10 raised power minus 6 amp. Milli means 2 cross 10 raised power minus 3 amp. So make sure you know the difference between milli, micro, macro, giga, and nano. So a complete circuit is one where current can flow all the way around. Note that this is just you can achieve this and do this in your daily life. For take a bulb and connect the two terminals with the battery. So if you have a bulb, you'll see that it will glow. Of course, it has to be a very small bulb for one single AA battery. So the circuit representation of the setup is for the battery we use a symbol plus minus, and for the device bulb, normally bulb is represented like this, and the direction of the electric current is shown with arrows. So we normally in a circuit we write down the symbol I, and here we write down the symbol delta V, or simply in some books you will see we write V. So do not confuse V with electric potential anymore, because we are talking about electrical current here. So the battery gives us potential difference, which in sometimes we write as delta V or simply V. So this formula of electrical current through, if we know the number of charges flowing, or if we know the current flowing, we can solve several problems with this. If I know that there is a 2.5 ampere current flowing, and if I know that the time taken for this to complete, the time taken to complete or light the bulb was 4.0 minutes or so, or if the current was on for 4.0 minutes, how many charges were flowing in the setup. So you know that we know that current is change in rate of change of charge. So if I have to find out how much charge was traveling in the circuit for 4 minutes, we can simply use this equation and multiply both sides by delta T and get I times delta T. So this answer should be in coulombs only. So I is 2.5 amperes and time is 4 minutes. 4 minutes is 4 times 60 seconds. So that would be 600 coulombs. That's a lot of charge. 600 coulomb is a lot of charge. And the charge on one electron is 1.6 cross 10 raised per minus 19 coulombs. If you have to find out how many electrons were traveling, if we could modify this, and we could say how many electrons were flowing through the circuit in 4 minutes. So we could simply say, oh, 600 number of charges flowing will be 600 coulombs over the charge of a single electron, 10 to the power of minus coulombs per electron. So if you divide this, we end up getting 3.8 cross 10 to the power of 21 electrons. So in a time of 4 minutes, the number of electrons that were traveling through the circuit which had a current of 2.5 amperes, is of the order of 3.8 cross 10 to the power of 21 electrons. So this is how we find out that it's a huge number. Electric current is a rate of change of number of electrons passing through a piece of conductor per unit time. Rate of change means divided by time. Next, we talk about several different types of connecting. In order for the current to flow, there must be a path from one battery terminal through the circuit and back to the other battery terminal. Only one of these connections will work. So incidentally, this doesn't seem to be a plausible connection because the other terminal is not connected. Again, this should also not glow. The only correct version is where you see that the bulb is connected, the positive and the negative are connected. So in figure A, there is no closed path for the charge to flow. And in B, there is a closed path, but it is not, it's not past, the wire is not touching the other terminal. So there's no potential difference. We need a potential difference. So it's also wrong. This is so that's why option C is the correct option, where you see that there's a closed path and the battery is connecting the bulb to both the terminals. So this scheme will light the bulb. So we again move to the slide where we talk about conventional current and the direction of the current. So by convention, we actually mean in many real circuits, wires are grounded and connected to common conductor that provides continuity. We also, you must have heard about the word grounding. The grounding actually, the symbol for grounding is used as, we show it as like this, which means the excess charge is flowing to the ground. In a car, one terminal of battery is called ground, but is not connected to earth itself. It is connected to the frame of the car, as is one connection to each light bulb and other devices. So when the conventions of positive and negative charge were invented 2 centuries ago, like in 1800s, it was assumed that positive charge flowed in a wire. For nearly all purposes, positive charge flowing in one direction is exactly equivalent to negative charge flowing in the opposite direction. So today we still use the historical convention of positive charge flow when discussing the direction of a current. So when we speak of the current direction in a circuit, we mean the direction positive charge would flow. This is sometimes referred to as conventional current. So we always mention to this as conventional current, but in our minds we know it's actually the electron flow is in the direction opposite to that of the conventional current. But when we draw the circuit diagrams, we always show the direction of the current as the conventional current. So in chapter 19, when we talk about circuits, that's what we will keep it in our mind. So it may be a good idea to work on one of the problems from your textbook. This is the very first one. A current of 1.6 amps is flowing in a wire. How many electrons are flowing past any point in the wire per second? So we already know that current is given by I is equal to delta Q over delta T. So here the time is 1 second and the current flowing is 1.60 amps. So you have to find out how many electrons are flowing past any point. It's similar to the example that we just discussed. In order to find out the charge, number of charges flowing, we know that we have delta Q is equivalent to N times E. I have to find the number N. E is the charge of the electron. So if I know I know delta T, so I can find delta Q. So delta Q is your I multiplied by delta T. The time is per second, so you have I is equivalent to 1.60 coulombs over second, which is 1.6 amperes. So you got your delta Q, and then you can go ahead and find out, equate it to N times E is equivalent to delta Q. N is equivalent to delta Q over the charge of an electron. We keep it as magnitude because we're talking about number, so we don't have to put it as negative. So we keep it as magnitude of the charge of an electron. And this is 1.60 coulombs. And divided by 1.6 cross 10 to the power of minus 19 coulombs. So you can see that the coulomb and coulomb goes away. So number has no unit. And we should end up getting 1.0 10 to the power of plus 19 is the number of electrons that were flowing through the wire per second. And once again, a similar problem here. What is the current in amperes if 1200 sodium ions, positive ions, flow across a cell membrane in 3.1 microseconds? 3.1 micro means 10 raised power minus 6 seconds, a very brief time. The charge on the sodium is the same as on the electron, but positive. So sodium ion is positive, but you know that positive and negative charges have the same magnitude. So the formula doesn't change here. We have to find I, which is delta Q over delta T. Time is given to you, and we are giving you 1200 sodium ions. So that is 12 number of, in fact, you can first write it as Q is equal to N times magnitude of E over delta T. So the magnitude of the positive and negative charge is same. We have 1200 sodium ions and charge on each of them 1.6 10 to the power of minus 19 coulombs divided by 3.1 cross 10 to the power of minus 6 seconds. So you should be, if you take out your calculators, pause the video and calculate this, you should be able to find out the current that is flowing through the cell membrane in 3.1 microseconds. You have to imagine the cells are really tiny and the information passes at lightning speed. So the current generated in this scenario should be of the order of 6.2 cross 10 to the power of minus 11 amps. It's a very small current that is generated in our cell membrane. Once again, we can talk about another question. How many coulombs are there in 75 ampere hour car battery? So when I say how many coulombs, that means I'm trying to find out delta Q, and what is given? I multiplied by delta T is given to you. So we know I is equivalent to delta Q over delta T. So therefore your delta Q must be equivalent to I times delta T. Right? So go ahead and work on this to find out the delta Q. So therefore your delta Q will be 75 amperes multiplied by 1 hour. So 1 hour, but you don't want to have an hour in the coulomb, and we want to have answer in seconds, only then we have the ampere in there. And 1 ampere is coulomb per second, so we'll come to that. 1 hour is, you want the 1 hour going away, and you know it is 60 minutes multiplied by 60 seconds. So you have 75. Instead of ampere, I can also write coulombs over second, because 1 ampere is 1 coulomb over 1 second, the SI unit of current. And you have 3600 seconds here. The second and second goes away, and you're left with 75 multiplied by 3600 coulombs. Go ahead and write this in scientific notation. So once you multiply, this should be of the order of 2.7 cross 10 to the power of 5 coulombs as delta Q. Next, we talk about Ohm's law. In Ohm's law is an experimental study, basically. In Ohm's law, they studied how resistance and how voltage and current depend on each other, and how do we find out what is the resistance offered by this circuit. To produce an electric current in a circuit, a difference in potential is required. So if I have a circuit and there's some bulb which has a resistance, and then we have a battery plus or minus, and in order for us to solve this, we need to know the current that is flowing through the circuit. We show the conventional direction from positive to negative, and if I say this is the resistance R, this could ideally be a bulb. So one way of producing a potential difference along a wire is to connect its end to the opposite terminal of a battery, so we can have the resistance. It was Greg Simon Ohm who established experimentally that the current in a metal wire is proportional to potential difference V applied to its end. So current is directly proportional to the voltage. Voltage is potential difference. Remember that. Do not confuse this letter V from previous chapter 17 to electric potential. This is electrical potential difference. Delta V is potential difference, which in this chapter onwards and 19th chapter also we will use simply as V. If, for example, we connect a wire of 6-volt battery to the terminals of a 6-volt battery, the current in the wire will be twice what it would be if the wire was connected to a 3-volt battery. So if I first use 6-volt battery and then I use 3-volt battery, obviously the higher voltage I use, the higher current that is generated in the wire. So this was experimentally studied and graphically recorded, and based on that, they said if I remove the proportionality, exactly how large the current is in a wire depends not only on the voltage between its ends, but also on the resistance that the wire offers to the flow of electrons. So electron flow is impeded because of collisions with the atoms of the wire, and this impediment of motion of electrons through the wire is called resistance, and the resistance is symbolically represented by R, and the unit of electrical resistance is ohm. The Greek symbol is like this, and we say it as OHM, ohm, just named after the scientist who worked on it. So once we remove the proportionality sign, we simply write V is equal to I times R. This is directly from there's no mathematical work needed to get to this equation. It was based on experimental evidence. You can also use I is equal to V over R. If you are finding current, you can use this form. If you're finding resistance, you can do V by I. So you can use this equation in 3 different forms depending on which equation you're needing, whether you want to find voltage, whether you're finding current, or you're finding resistance in a circuit. And Ohm also plotted the graph between I versus V, and he found that there was a direct relationship, linearity, like of the order, linear fit is mx plus c or mx plus b. So m represents the slope. The slope over here represents our 1 by r. That is the inverse of the resistance. So for all devices, for all metal conductors, all metal conductors obey Ohm's law. So I versus V or V versus I. We can plot it either way. We get a straight line, slope of a straight line y is equivalent to mx plus b. The slope m is simply r if I plot V versus I. For all metallic conductors, the slope will always be r, and the graph between V and I will be a straight line. I could also plot I versus V, and that would also be a straight line, but the slope m would be inverse 1 by r. We simply follow V is equivalent to I times r. So if you are using V is proportional to I, if I remove the proportionality, I have to insert a constant, and that constant for that particular conductor is R, the resistance. Then there are different categories of materials that we call non-ohmic conductors. Non-ohmic conductors like LEDs, diodes. They don't follow Ohm's law. The current and voltage do not have a linear graph. So it can kind of, at a particular voltage, there's an exponential increase in the rise of the current. So non-ohmic device, like a semiconductor device, will not follow Ohm's law. You just have to remember that. Other ways of understanding resistances. So there is a way in which in the labs we have some resistances that are used in digital circuits, is the way of color coding. If you have seen your devices, if you open some device, you'll see a circuit board, and the circuit board has different components in it, like capacitors, resistances, and all. And then the resistances are inserted in the circuit, which actually try to stop the excess flow of current. Capacitor also stores the charge. So the resistances are color coded, and each color has its own number based on the chart that we have. And the striped, the first color represents the first digit in the multiply, in the, like if it is 100 ohms, the first color will represent that number. If the second number will represent whatever number is over there. It's not necessarily the green represents a 0, but I'm just giving you an example. And the third one represents the multiplier. So if it is 100 multiplied by 10 raised power 1, so it can be 10 raised power 1 ohms. The multiplier is what is the exponential term that you have on 10. So, and the last one is tolerance, which is plus minus 2% or 3% for gold, silver. There is different tolerance level. So we will take a quick look at the chart to understand this, and then look at an example as well. So in this case, the first digit on the chart, we have, for example, we have red. On the chart, red is 2. So we'll go back, and the resistance value, first digit is 2. The second color is green. We'll go and look at the green color, and the green color is 5. So we write the second digit. The third one is the multiplier, 10 to the power, yellow. We'll see what is yellow. So yellow is 4. So we go ahead and put 10 raised power 4 over it. And then we say, okay, this much ohms, the resistance of this type of resistance is 25 cross 10 raised power 4 ohms. But we are not done yet. We can also represent it as 250 kilo ohms, or we can also, and also the silver has a tolerance. So silver has a tolerance of 10%. So this represents plus minus 10% tolerance for silver. It's an alternative code in that the tolerance means like it's your value can be between less or a great less than 10% or more than 10%, and the value can lie in that. For example, a resistor whose four colors are red, green, yellow, and silver in this case, plus or minus 10%, the value stretches between these. So this is how, if I give you a resistance and ask you to use the table to find the value of the resistance. The other way is to use a multimeter, a device which, when directly connected to the resistance, gives the value. That's the easiest way to do it. And in our circuit, the symbol of the resistance is generally given as a symbol like this, and the direction of the current I is shown to flow like this. If it's terminal A and B of the resistance, the direction of the current can be shown this way. If the positive of the battery is connected here and negative, and the current flows this way and enters back the circuit this way. This is the conventional direction, and we show the loop like this. So positive charge always flows from positive to the negative, from high potential to low potential. So if current I is conventional, that is positive current, point A is at a higher potential than point B. And conservation of charge requires that whatever charge is flowing into the resistor at point A, an equal amount of charge emerges at point B, that's over here, and hence once it returns back to the negative of the terminal, the number of charges used up are retrieved back, and hence the cycle goes on and on. So the current at A and current at B point in this setup is going to be same. So some clarifications. Batteries maintain a nearly constant potential difference. The current can vary. Resistance is a property of a material or a device, not of the battery. Current is not a vector, but it does have a direction because of the way we draw our circuits, like conventional direction. Current and charge do not get used up. Whatever charge goes in one end of the circuit also comes out of the other end, just like we showed in our sample electric circuit. So let's work on one of the problems from your textbook. So a bird stands on a DC electric transmission line, as is shown in the figure. The line has a resistance of 2.5 cross 10 raised power minus 5 ohms. Just by looking at the units, you can tell whether it is a current or a voltage. So obviously we have the unit ampere here, so this must be the current flowing through the wire, really high transmission line. And the resistance, very low resistance of 2.5 cross 10 raised power minus 5 ohms. Resistance per meter, and the bird's feet are 4 centimeters apart. What is the potential difference between the bird's feet? So first of all, the resistance R is 2.5 cross 10 to the power of minus 5 ohms per meter. Ohms per meter. And 4 centimeters apart. So you are trying to find out the resistance between this length of the, this width of the, where it's standing. So we kind of multiplied by 4 centimeters apart. So 4.0 cross 10 to the power of minus 2 meters. So in other words, the resistance R will be 2.5 cross 10 raised power minus 7 ohms. Sorry, minus 5 and minus 2 combined to give us, actually we have to multiply it by 4 as well. So the overall answer 4.0 multiplied by 10 raised per minus 5 cross 10 to the power of minus 2. When you work on this, you should end up getting 1.0 cross 10 to the power of minus 6 ohms as the resistance for that stretch. So then you have to find out the voltage between the two ends of the feet, between the bird's feet. We know from Ohm's law, V is equal to I times R, and the current that is passing through this wire is the same. So you have 4,100 ampere current, and the resistance between the bird's feet based on its length, width of separation, 10 to the power of minus 6 ohms will give you the voltage, that is, the unit should be volts. So it gives you a voltage of 4.1 cross 10 to the power of minus 3 volts, which is not a big voltage if you look at it. It's a 4.1 millivolts, and hence the bird probably is alive because of low voltage. It's a millivolt, or we can also say 4.1 millivolt voltage. So the next problem we look at is another one based on Ohm's law. And an electric device draws 5.60 amps, that's the current, at 240 volts. And you're asked to, if the voltage supply drops by 15%, what will be the current, assuming nothing else changes? B part, if the resistance of the device were reduced by 15%, what would be the current drawn? So if you reduce the voltage, what would be the effect? If you reduce the resistance, what will be the effect? So part A, if the voltage is dropped by 15%, 15% is out of 100, if you drop 15, it is 85. So 85% means 0.85. So I final, if I drop by 15% is I initial. So how much of this current will it be? So it will be 0.85 times the initial, which is 5.60 amps. So the final current is definitely lesser, which is 4.8 amps. In the same way, let's check if the resistance drops by 15%, the same as being multiplied by 0.85, and the voltage stays the same. So what will be the voltage final? So we are finding what current would be drawn at 240 volts if the resistance of the device were reduced by 15%. So what current would be drawn at 240 volts? Current I is also V by R. So if voltage is 240 and resistance is dropped by 15%, so you can say I final must be equivalent to I initial over 0.85. So because if the resistance drops by 15%, the same as being multiplied by 0.85, and the voltage stays the same, then the current must be divided by 0.85. So that's 5.60 amps over 0.85, which gives me higher current. If resistance drops, the final current increases. This shows the inverse proportionality between current and resistances. If current increases, resistance decreases, and if resistance decreases, current increases, and vice versa.